Hello and welcome to Class 18 on Paramagnetism and Diamagnetism. We've been concentrating a lot on the production of magnetic fields and the description of magnetic fields using the multipole expansion and the vector potential, but we haven't spent much time looking at the effect of magnetic fields on materials, which is an important piece of physics and engineering. This material comes from section 6.1. So paramagnetism and diamagnetism are the two dominant effects that a magnetic field can have on a material. So paramagnetism has to do with torques on magnetic dipoles. But first, before we get into that, when most people think, and you probably think of magnets like a refrigerator magnets, you're actually thinking of something called a ferromagnet, ferro being the Latin prefix for iron, which is the most common component of ferromagnets. And ferromagnets are the strongest magnets. The atoms inside a ferromagnet actually have an interaction between their magnetic moments, which tends to make them align together and create a very strong and a widespread unidirectional magnetism, so that the whole ferromagnet acts as one. Although the effects of temperature can destroy ferromagnetism, the temperature required to break this collective magnetic attraction of the atoms for each other is quite high. Iron maintains its magnetism up over 1,000 kelvins. So those are ferromagnets: iron, nickel, and cobalt, and some ceramic materials. Most substances respond magnetically, but much more weakly than ferromagnets, but nevertheless significantly. So paramagnetism is where magnetic moments align with the field, and it results from torques on unpaired electron spins. You may remember from modern physics, or perhaps in quantum mechanics, if you're taking it, that electrons have this property called spin, and associated with the spin is a magnetic moment. And if the rules of quantum mechanics actually say that spins tend to occupy orbitals or wave functions in pairs, where the up and down spins magnetism cancels. So it's the unpaired electron spins that tend to respond to magnetic fields. This here is a model of a magnetic moment, which could be coming from an electron spin. And it's macroscopically, that magnetic moment would come from a loop of current. In the electron, there's actually no loop of current which is producing this. It's an intrinsic property of the electron. So what would be the magnetic moment effect on the magnetic moment of this magnetic field? Well, we can use the Lorentz force equation to figure out the force on this side. It's going to be I L cross B, as we learned in a previous lecture. And I is just given by I. L is given by, here in this figure, by little b. And B is given by big B. And L is cross B. They're perpendicular. So the magnitude would just be, of the force would just be I times little b times big B. And that force is going to be exerted by the right-hand rule to the left on this side and to the right on this side. So that's going to have a tendency to rotate the loop counterclockwise, around the x-axis. The torque, remember torque is given by the lever arm times the force. The lever arm here would be A times the sine of theta for this applied force. It would be A times the sine of theta. And the force applied would be, A right here times the sine of theta is this distance right here. That's the lever arm. And the force is F. So, and the direction of the torque, as we said, which is represented by N in our textbook instead of tau. So N is the torque, would be counterclockwise. So plugging in the force F, I little b big B for F, we get IAB times capital B times the sine of the theta x hat. You may recognize I times A times B. Well, A times B is the area of this loop, and I, the current times the area, is what we called in the previous lecture on magnetic multipole the magnetic moment. So the magnetic moment is IAB, and so we have MB times sine theta x hat. Then M and B are both vectors, and we might recognize that the formula for the length of a cross product is the length of two vectors times the sine of the angle between them. And this is a vector. And so indeed, we haven't proved it for all general directions, but it turns out that the torque on a magnetic moment exerted by a magnetic field is just M cross B. Very, very simple, very satisfying formula. Okay, we haven't fully derived that, but we've derived it for this specific case, and it turns out to be true in general. So what does that torque do? Well, we've seen that the torque tends to rotate the loop counterclockwise, which tends to bring the magnetic moment into alignment with the magnetic field. And that's if we apply a stronger magnetic field, we're going to get more magnetic moments in the direction of that field, and the magnetization will increase in the same direction as we apply a field. That's a paramagnet. Incidentally, the net force on the current loop, as opposed to the torque, is 0. We can see that if we look at the forces on the individual sides here using the Lorentz Force Law. But an easier way to see it is just to say that the force is equal to, according to Lorentz Force Law, I times the integral of dl cross b, which is like qv cross b. Units of idl are the same as the units of q times v. And then since b is constant, we can pull it out of this integral, and we just get I times the line integral of dl around the loop cross b. But the line integral of dl is 0 since we're looping around to where we started. Okay, so a paramagnet is a substance such that applying a magnetic field in a certain direction increases the magnetization in that direction. A diamagnet, as you might suspect, is like diabolical, sort of does the opposite of what you would hope or expect. It has the opposite effect. If we apply a magnetic field to a diamagnet, the magnetic moment increases in the opposite direction. And rather than being due to the effect of the magnetic field on electron spins, it's due to the effect of the magnetic field on atomic orbits. So here is a model of an electron circling an atom, and we have the electron's charge minus the elementary charge. It's at a radius r. It's traveling at speed v. Its angular momentum would be m or mvr, pointing in the positive z hat direction, because it's r cross m times r cross v. But the magnetic moment, since the charge is negative, is in the opposite direction from the angular momentum. So the magnetic moment here would point downwards. Okay, so as I said, diamagnetism, where magnetic dipoles are shifted opposite the applied field, is due actually to a change in the speed of the electrons as they circle around these orbits. Now, just a quick word, you may be aware from quantum physics, in modern physics, or in quantum mechanics, that this is electrons don't orbit in circular paths like this, that they're in probability clouds. But nevertheless, considering this circular path gives us a nice picture of what a sufficient picture of to get a qualitative idea of how diamagnetism works. So just to get quantitative, the current is equal to minus the charge over the period, which is minus E over t. And the period t would be the distance traveled, which is the circumference over the velocity. So that flipping that, the circumference goes in the denominator and the velocity goes in the numerator. So the current is minus EV over 2 pi r. The magnetic moment is therefore going to be the current times the area, and the area is pi r squared. So if we multiply this, you can check by pi r squared, we get minus 1/2 EVR. The r squared cancels, one of the r's cancels, and the pi cancels. So we have minus 1/2 r z hat is the relationship for the magnetic moment of the electron circling around. Okay, so what keeps the electron circling around? Well, it's electrical forces. That's true in quantum physics as well. Classically, we would say that we use Newton's law, F equals ma, and we're going to treat this classically, just as an approximation. The attractive force is the Coulomb force, which is this, 1 over 4 pi epsilon naught E squared over R squared. That's equal to me, the mass of the electron, times V squared over R. Now, supposing that we apply a magnetic field in the upward direction, perpendicular to the plane of the orbit, what's going to happen? Well, according to Lorentz Force Law, with the magnetic field upward and the electron here circling around counterclockwise, so the electron tangentially would be going into the screen, we would have a magnetic force, since the electron's a negative particle, toward the center. Okay, so an upward magnetic field would create a magnetic force toward the center. So we get a positive force in the same direction as the electrical force, equal to QVB, where Q being the charge on the electron, and V now written as V bar, because it may be a different velocity. In fact, the velocity of the electron will get faster since there's more force on it. And so that's going to be equal to me times the new V bar squared over R. So notice we can, these have a common term, so we can subtract these two equations, subtract the first from the second. And when we do that, on the left-hand side, we're just left with EV bar B. On the right-hand side, we get ME times V bar squared over R minus V squared over R, just factored out the R here. And then notice that this is a, from algebra, we can write this as V bar plus V times V bar minus V, right? Because if we apply FOIL to this, we get this expression right here. So now, often the V bar does not change very much from V because the magnetic force is a lot weaker than the electrical force. So V bar and V are very close, and therefore delta V, V bar minus V is small, and V bar plus V is approximately equal to just twice V bar. Okay, so we can replace V bar plus V with twice V bar, and we can replace V bar minus V with delta V, and we get dividing by 2V bar over here, and multiplying up by R, dividing by ME, we can solve for delta V, and it's it's ERV over 2ME. Okay, final step. We know that the magnetic moment is minus 1/2 EVRZ hat. It points opposite the direction of the velocity. We see that the magnetic field has increased the velocity, and so the change in the magnetic moment is going to be just minus 1/2 E times delta V times R Z hat. And notice already that this points in the direction, the minus Z hat direction, opposite the direction of the applied magnetic field upward. So we've already established diamagnetism. If we like, we can plug in this expression for delta V here and get an expression just in terms of the parameters of the orbit, the charge, the radius, and the mass. So that's diamagnetism, and it has to do with the fact that an applied magnetic field speeds up the electron in its orbit, and therefore increases the magnetic moment opposite the applied magnetic field. So a couple of concluding remarks. It's not as if a given substance is purely paramagnetic or purely diamagnetic, because all substances have at least some degree of exposed electron spin and certainly atomic orbitals. So all substances, including ferromagnets, possess some paramagnetism and diamagnetism. It's whichever is the stronger effect of the two determines whether we call it a paramagnet or a diamagnet. And then finally, as I've mentioned a couple times, this video has presented a classical, or some might say a semi-classical picture of the electron spin and the atomic orbital. An accurate picture actually has to be done quantum mechanically, and we can get more accurate coefficients for the paramagnetism and diamagnetism of different substances. But nevertheless, this gives us more direct physical insight into why some substances, why paramagnetism and diamagnetism exist, and why we have some substances that respond in the same direction as the field and others that respond opposite. All right, thank you very much for listening, and I will see you in class.